Introduction. In Greek mythology, Pandora's box symbolized the release of forces that humanity could neither fully understand nor easily control. Once opened, the contents could not be returned to their container. The metaphor remains remarkably relevant in the 21st century as artificial intelligence advances at a pace that few anticipated even a decade ago. Recent developments from leading AI laboratories, particularly Anthropic's Mythos initiative and OpenAI's GPT-5 for cyber capabilities, have reignited discussions about whether humanity is approaching a technological threshold from which there is no retreat. Both Anthropic and OpenAI have partially unleashed what may be described as a modern Pandora's box. Debates will undoubtedly continue regarding which organization's approach is more sophisticated, responsible, or strategically nuanced. Anthropic has reportedly restricted access to a highly exclusive cohort through Project Glasswing, while OpenAI has expanded availability to a somewhat broader network of trusted partners. Neither strategy can be declared inherently superior. Both represent attempts to navigate a rapidly evolving landscape in which the opportunities and risks of advanced artificial intelligence are becoming increasingly difficult to separate. The significance of these developments extends far beyond the competitive ambitions of two technology companies. At stake is the emergence of systems capable of autonomous reasoning about software, identifying vulnerabilities, repairing code, and potentially discovering weaknesses across complex digital infrastructures. Such capabilities represent more than incremental improvements in automation. They signal the possible beginning of a new computational epoch, one in which software increasingly becomes both the subject and object of its own intelligence. The implications are profound, far-reaching, and potentially existential. The evolution of artificial intelligence from tool to agent. Historically, software has functioned as an instrument. Humans designed programs, tested them, corrected errors, and deployed updates. Even the most sophisticated automation systems ultimately depended on human intervention at critical decision points. Artificial intelligence, particularly in its modern generative form, has begun to challenge this paradigm. The distinction between traditional software and advanced AI systems lies not merely in complexity but in agency. Contemporary large language models can analyze source code, explain vulnerabilities, generate patches, and propose architectural improvements. Increasingly, they can perform these tasks with minimal human supervision. This evolution represents a transition from software as a passive tool to software as an active participant in technological ecosystems. The prospect of autonomous code generation was once considered speculative. Today, organizations routinely employ AI-assisted development environments that generate significant portions of production-ready software. The next logical progression is autonomous maintenance, systems that not only write code but also monitor, diagnose, and repair it. Such developments promise extraordinary gains in productivity. Software defects cost organizations billions annually through outages, security incidents, and maintenance expenses. An AI capable of continuously identifying and correcting these defects could dramatically improve reliability and efficiency. Yet every technological advance carries unintended consequences. The same system that can identify and repair vulnerabilities can also identify and exploit them. The rise of self-repairing software. Perhaps the most transformative aspect of current AI research is the emergence of self-repairing software systems. For decades, software engineering has struggled with the challenge of complexity. Modern enterprise applications often contain millions of lines of code distributed across multiple environments, programming languages, and infrastructure layers. Human developers face significant limitations in comprehensively understanding and maintaining such systems. Artificial intelligence offers a fundamentally different approach. Rather than relying exclusively on human review, advanced AI systems can continuously analyze codebases, identify anomalies, predict failures, and generate corrective actions. Future systems may monitor their own execution states, recognize deviations from expected behavior, and automatically initiate remediation procedures. The implications for cybersecurity are particularly significant. Imagine an enterprise platform that detects an emerging vulnerability, develops a patch, validates the solution against regression tests, and deploys the correction without waiting for human approval. Such a system could dramatically reduce the window of exposure between vulnerability discovery and remediation. From a defensive perspective, this capability appears revolutionary. However, autonomy introduces a new set of challenges. What happens when the AI misidentifies a vulnerability? What safeguards prevent unintended modifications to mission-critical systems? How do organizations audit decisions made by increasingly opaque machine learning models? These questions illustrate a broader reality. Self-repairing software may solve many existing problems while simultaneously creating entirely new categories of risk. Cybersecurity in the age of autonomous intelligence. Cybersecurity has traditionally been characterized as an asymmetrical contest between attackers and defenders. Attackers need to discover only a single exploitable weakness, whereas defenders must secure every potential entry point. Artificial intelligence has the potential to alter this dynamic fundamentally. Advanced models can evaluate vast quantities of code far more rapidly than human analysts. They can identify subtle vulnerabilities, recognize insecure design patterns, and simulate attack scenarios across complex systems. Defensive applications include vulnerability management, threat detection, incident response, and security architecture review. Yet the same capabilities can be weaponized. An AI system trained to identify vulnerabilities can potentially assist malicious actors in discovering attack vectors at unprecedented speed and scale. While safeguards and access controls can reduce this risk, they cannot eliminate it. Once a capability exists, the possibility of misuse inevitably accompanies it. This dual-use characteristic has long been recognized in fields such as nuclear physics, biotechnology, and cryptography. Artificial intelligence now joins this list of transformative technologies whose benefits and dangers are inseparably linked. The challenge is not simply technical but societal. Policymakers, researchers, and industry leaders must determine how such systems can be developed responsibly without stifling innovation. Achieving this balance may prove one of the defining governance challenges of the 21st century. The problem of scale. One of the most striking features of contemporary AI development is the extraordinary speed at which progress occurs. Technological revolutions historically unfolded over decades. The Industrial Revolution transformed societies across generations. The rise of personal computing spanned multiple decades before reaching maturity. Even the Internet required years before becoming ubiquitous. Artificial intelligence appears to be advancing on a compressed timeline. Capabilities that seemed improbable 2 years ago are now operational realities. Models continue to improve in reasoning, planning, coding, and problem-solving. Computational resources, training methodologies, and data availability continue to expand. This acceleration creates significant governance difficulties. Regulatory frameworks move slowly. Academic research often requires extensive validation cycles. Corporate compliance structures are not designed for technologies whose capabilities evolve every few months. As a result, society may find itself attempting to regulate systems that are already substantially more capable than those originally evaluated. The pace of innovation, therefore, becomes a risk factor. The challenge is not merely understanding what AI can do today. It is anticipating what AI may be capable of tomorrow. Competitive dynamics and the concentration of power. An equally important dimension of this discussion concerns the competitive environment surrounding advanced AI development. The creation of frontier AI systems requires immense computational resources, specialized expertise, and substantial financial investment. Training state-of-the-art models demands infrastructure that only a handful of organizations can afford. Consequently, the frontier of AI development is increasingly concentrated among a small number of exceptionally well-funded institutions. Anthropic and OpenAI represent two prominent examples. Their differing access strategies reflect distinct philosophies regarding risk management and deployment. One emphasizes exclusivity and controlled experimentation, the other seeks broader collaboration with selected partners. However, beneath these strategic differences lies a shared reality. Both organizations operate within an environment characterized by intense competition. Success in frontier AI development confers enormous economic, strategic, and geopolitical advantages. The incentives to advance rapidly are therefore substantial. This dynamic resembles an arms race in several respects. Each breakthrough creates pressure for competitors to achieve comparable or superior capabilities. Safety considerations remain important, yet they must coexist with commercial realities and investor expectations. The result is a persistent tension between caution and acceleration. Importantly, this contest is one that only the wealthiest organizations can realistically sustain. Smaller institutions, independent researchers, and many academic laboratories lack the resources necessary to compete at the highest levels. The concentration of technological power raises critical questions regarding accountability, transparency, and democratic oversight. 1. Who should control technologies capable of influencing global cybersecurity? 2. Who determines acceptable levels of risk? 3. And who bears responsibility when autonomous systems fail? These questions remain largely unresolved. Existential considerations. The term existential risk is frequently used in discussions of advanced artificial intelligence, though often without a precise definition. In this context, existential concerns do not necessarily imply science fiction scenarios involving hostile superintelligences. Rather, they refer to the possibility that AI systems may fundamentally reshape critical aspects of human society in ways that are difficult to predict or reverse. Consider a future in which autonomous systems manage substantial portions of global digital infrastructure. Financial networks, healthcare systems, energy grids, transportation platforms, and communication systems could all become increasingly dependent upon AI-driven operations. Such systems might offer unprecedented efficiency and resilience. At the same time, failures could become correspondingly more consequential. A vulnerability introduced into a widely deployed autonomous platform could propagate rapidly across interconnected networks. Errors could scale at machine speed rather than human speed. Decision-making processes might become difficult for operators to understand or audit. The concern is therefore not simply whether AI can make mistakes. Human beings already make mistakes. The concern is whether AI can make mistakes at a scale, velocity, and complexity that exceeds humanity's capacity to respond effectively. Beyond optimism and pessimism. Public discourse surrounding artificial intelligence often oscillates between extremes. On one side are technological optimists who view AI as the solution to virtually every societal challenge. On the other are critics who regard advanced AI primarily as a source of risk and disruption. Both perspectives capture important truths while overlooking critical nuances. Artificial intelligence possesses extraordinary potential. It may accelerate scientific discovery, improve healthcare outcomes, enhance cybersecurity, and increase productivity across numerous sectors. Simultaneously, it introduces genuine risks involving security, governance, employment, privacy, and systemic stability. A mature assessment requires acknowledging both realities. The question is not whether AI is inherently good or inherently bad. Technologies rarely fit such simplistic categories. Rather, the crucial issue is how societies choose to design, deploy, regulate, and govern these systems. The future will be shaped not solely by technological capability but by institutional wisdom. Conclusion. The emergence of initiatives such as Mythos and GPT 5.4 Cyber symbolizes more than another milestone in artificial intelligence research. These developments represent a broader transformation in the relationship between humans, software, and autonomous decision-making systems. Whether one prefers Anthropic's more restrictive deployment model or OpenAI's somewhat broader partner-based approach is ultimately a secondary question. The larger reality is that both organizations are exploring capabilities that could fundamentally alter cybersecurity, software engineering, and technological governance. Self-repairing code, autonomous vulnerability discovery, and AI-driven system optimization are no longer speculative concepts. They are becoming practical realities. Their potential benefits are immense, but so are their risks. Pandora's box, once opened, cannot easily be closed. The challenge before researchers, policymakers, industry leaders, and society at large is not determining whether these technologies should exist. That question has already been answered. The challenge is determining how they should be managed. As artificial intelligence continues its rapid ascent, humanity faces a defining choice. We can approach this new era with rigor, transparency, and thoughtful governance, or we can allow competitive pressures and technological momentum to dictate the future by default. The stakes extend beyond individual companies, products, or market valuations. They concern the architecture of the digital world itself, and perhaps the future trajectory of human civilization.